Welcome to today's paper reading. Today's paper is titled, Graph Machine Learning in the Era of Large Language Models, LLMs. This paper, authored by Wenqi Fan and colleagues from the Hong Kong Polytechnic University, Wuhan University, Michigan State University, North Carolina State University, and Baidu Incorporated, was submitted to the IEEE Transactions on Knowledge and Data Engineering in 2023. Graphs are crucial for representing complex relationships across various domains, including social networks, knowledge graphs, and molecular discovery. With the rise of deep learning, graph neural networks, GNNs, have become foundational in graph machine learning, graph ML, enabling effective representation and processing of graph structures. Recently, large language models, LLMs, have shown remarkable capabilities in language tasks and are increasingly being applied to the graph domain. Efforts are being made to leverage LLMs to enhance graph ML's generalization, transferability, and few-shot learning abilities. Additionally, graphs, particularly knowledge graphs, offer reliable factual knowledge that can augment LLM's reasoning capabilities and address limitations such as hallucinations and lack of explainability. This survey aims to provide a comprehensive review of the latest advancements in graph ML with the integration of LLMs, offering insights for researchers and practitioners. The introduction of this paper highlights the widespread use of graph data in various real-world applications such as social graphs, knowledge graphs, and recommender systems. Graphs typically consist of nodes and edges, with nodes representing entities and edges representing relationships. Graph machine learning, graph ML, has gained significant interest for effectively modeling these graphs. With the advent of deep learning, graph neural networks, GNNs, have become critical due to their message passing mechanism, which allows nodes to aggregate information from neighboring nodes, capturing high-order relationships. Additionally, the paper discusses the recent integration of large language models, LLMs, into graph ML, showcasing their potential to enhance the generalization capabilities of graph ML towards graph foundation models, GFMs. LLMs, with their extensive scale and capabilities in natural language processing, are expected to play a crucial role in advancing graph ML by enhancing feature quality and addressing training limitations. Figure 1 illustrates the application of large language models, LLMs, in graph machine learning. The integration of LLMs with graph neural networks, GNNs, is utilized to model an extensive range of graph data across various downstream tasks. This integration aims to enhance the capabilities of GNNs by leveraging the semantic understanding and reasoning abilities of LLMs, thereby improving the modeling of complex graph structures and their features. Figure 2 outlines the structure of the survey on graph machine learning in the era of large language models, LLMs. Section 3 delves into the development of deep neural network, DNN-based methods, focusing on backbone architecture, graph pretext tasks, and downstream adaptation. Section 4 explores how current LLMs contribute to graph machine learning, graph ML, by enhancing feature quality, addressing training limitations of vanilla graph neural networks, GNNs, and handling heterophyly and generalization. Section 5 examines knowledge graph, KG, enhanced LLM pre-training and inference. Section 6 presents various applications, including recommender systems, knowledge graphs, AI for science, and robot task planning. Section 7 discusses future directions such as generalization and transferability, multimodal graph learning, and trustworthiness and efficiency. In the field of graph machine learning, initial techniques such as random walks have been foundational for exploring graph structures. Building on this, graph embedding methods like line, deep walk, and node2vec have been developed to represent nodes as low-dimensional vectors. More recently, graph neural networks, GNNs, including GCNs, GraphSage, and GT have significantly advanced graph learning capabilities. On the other hand, foundation models represent a breakthrough in AI, with visual foundation models, VFMs, excelling in image tasks and large language models, LLMs, revolutionizing NLP. These models, such as GPT and BERT, have diverse applications and are increasingly integrated with other models. However, graph foundation models, GFMs, are still in their early stages, yet hold significant potential for enhancing graph machine learning. Continued exploration of advanced techniques is essential for this field. In this section, we delve into the backbone architectures of deep learning on graphs, focusing on two primary models: neighborhood aggregation-based models and graph transformer-based models. Neighborhood aggregation models, such as GCN and GraphSage, are widely used due to their efficiency in capturing local graph structures. However, they face challenges like oversmoothing and limited generalization. On the other hand, graph transformer models, inspired by NLP transformers, leverage self-attention to capture both local and global graph structures, addressing some of the limitations of traditional GNNs. Despite their advantages, graph transformers also face challenges such as quadratic complexity with self-attention. Additionally, we explore self-supervised learning methods for graphs, including graph pretext tasks and downstream adaptation strategies like unsupervised representation learning, fine-tuning, and prompt tuning. These methods aim to enhance the adaptability of GNNs to various graph tasks, such as node classification and graph classification. Table 1 provides a detailed comparison of various deep neural network (DNN)-based models used in graph machine learning. The table categorizes these models based on their architecture, pretext tasks, adaptation methods, and the specific downstream tasks they are applied to. Notably, the adaptation method column includes URL, which signifies unsupervised representation learning. The downstream tasks listed encompass a range of applications from node and edge tasks to more complex graph-level tasks. This comprehensive overview is crucial for understanding the diverse applications and methodologies within the field of graph machine learning. Figure 3 illustrates the differences between pre-training, fine-tuning, and prompt tuning in adapting GNN models. Pre-training involves training the GNN model based on specific pre-training tasks. Fine-tuning updates the parameters of the pre-trained GNN model according to the downstream tasks. Prompt tuning generates and updates the features of the prompt according to the downstream tasks, while keeping the pre-trained GNN model fixed and without any modification. In this section, we explore the application of large language models, LLMs, in enhancing graph machine learning, GraphML. Firstly, we discuss the generation of augmented information. Methods like tape leverage LLMs to generate potential node labels and explanations, while KA focuses on extracting terms from textual attributes. LLM4Mol and GPT-MoBRTA generate interpretations for Smiles notations. Secondly, we look at enhancing feature representation. TouchUpG introduces a graph-centric fine-tuning strategy, and OFA provides a unified framework for classification tasks across different domains. The graph prompting paradigm is also introduced to adaptively perform tasks. Lastly, we address the limitations of vanilla GNN training. This includes methods that ignore structural information, implicitly describe structural information, and explicitly encode graph structure. Figure 4 illustrates the application of large language models, LLMs, in graph machine learning, GraphML. It categorizes methods into three main areas: enhancing feature quality through better representation, generating augmented information, and aligning feature space, addressing vanilla GNN training limitations by processing structural information in different ways, and alleviating issues related to heterophyly and generalization. This figure provides a comprehensive view of how LLMs are being utilized to improve various aspects of GraphML. Table 2 provides a comprehensive summary of research focused on integrating large language models, LLMs, with graph machine learning, GraphML. The table details various aspects of this research, including the specific graph neural network, GNN, models used, the LLM models, predictors, domains of application, tasks addressed, datasets utilized, and project links. Key terms such as FT, fine-tuning, NPR, prompting, are explained, indicating whether the LLM parameters were modified and whether textual prompts were used to elicit responses. The tasks are categorized into node level, edge level, graph level, and structure understanding tasks, providing a clear framework for understanding the scope of the research. Figure 5 illustrates the two main approaches of employing LLMs with structural information in graph tasks. The first approach, using implicit structural information, involves describing nodes and graph structure in natural language, combined with task-specific instructions to form a textual prompt. This prompt is then input into the LLM to generate prediction results. The second approach, using explicit structural information, involves separately encoding graph and instruction information using GNNs and LLMs. Fusion layers are then added to align the graph and text modalities, and the fused embedding is input into the LLM for prediction. In this section, we explore the advancements in KG-enhanced pre-trained language models, PLMs. The research can be categorized into three main approaches: modifying input data, modifying model structures, and modifying pre-training tasks. For input data modification, methods include training PLMs on mixed corpora of KG triples and natural language texts, aligning entity vectors with BERT's word-piece vector space, and constructing sentence trees with integrated triples. In terms of model structure modification, studies introduced knowledge-specific encoders or fusion modules, such as the K-encoder in ERNIE and the semantic-driven GNN model in Coke-BERT. Additionally, some research proposes knowledge aggregator modules to fuse text and KG modalities. Lastly, modifying pre-training tasks involves entity-centric tasks like predicting masked entities, relation-centric tasks for enhancing knowledge modeling, and innovative tasks like knowledge embedding to improve knowledge awareness of PLMs. In the realm of recommender systems, LLMs are being utilized for direct recommendation tasks, enhancing traditional graph models, and developing foundation models. Knowledge graphs benefit from LLMs in tasks like completion and question answering, with frameworks like LLM-KG Bench aiding in evaluation. In AI for science, LLMs are applied in drug discovery, molecular property prediction, and the development of specialized dialogue models like ChemDFM. In this section, we explore several future directions for graph machine learning, GraphML, enhanced by large language models, LLMs. Firstly, addressing the challenge of generalization and transferability, where current models struggle to perform optimally across diverse graph structures. Future research should focus on creating more adaptable models that can apply learned patterns from one graph type to another without extensive retraining. Secondly, multimodal graph learning, where the integration of various data modalities like text, images, and videos can significantly enhance graph learning capabilities. Developing a unified model capable of processing and integrating these multimodal data is a promising direction. Lastly, ensuring the trustworthiness of these models is crucial, particularly in critical areas such as healthcare and finance. This involves enhancing robustness against adversarial attacks, improving explainability to make model decisions more transparent, ensuring fairness to avoid biases, and protecting privacy to maintain user trust. In this survey, the authors have thoroughly reviewed the recent progress of graph applications and GraphML in the era of LLMs. They first reviewed the evolution of GraphML and then delved into various methods of LLMs enhancing GraphML. Due to the remarkable capabilities in various fields, LLMs have great potential to enhance GraphML towards GFMs. The authors further explored the augmenting of LLMs with graphs, highlighting their ability to enhance LLM pre-training and inference. Additionally, they demonstrated the potential in diverse applications such as molecule discovery, knowledge graphs, and recommender systems. Despite their success, this field is still evolving and presents numerous opportunities for further advancements. Therefore, the authors discuss several challenges and potential future directions. Overall, their survey aims to provide a systematic and comprehensive review to inspire future explorations in this promising field. Thank you for watching.